Hello everyone and welcome. Today we're going to solve another dynamic programming example using SESV, and our example today is house wrapper. House wrapper example fall into a few choices category. In our particular case, it's going to be two choices. The pace of solving our example today is going to be a little bit faster. So make sure you have learned about the modern law of dynamic programming, part 1 and 2. This tutorial is a part of the data structures and algorithms class. First, let's get to know our problem and see if it's a dynamic programming problem, or in the other word, and see if it's a multi-stage decision-making process problem. House wrapper is Leetcode number 198. We are given n houses, and the rule is we cannot wrap two adjacent houses. Each house has different money in them. If we wrap one house, we're going to get the money that the house has. For example, in this case, the first house has $1, the second house has $3, and the third house has $4. And the question is, what is the possible max amount of money that we can wrap? In this example, we have three houses with the money in them as an array of 1, 3, and 4 respectively. And as we cannot wrap two adjacent houses, we can see that wrapping the first house and the last house is going to give us $5. And that is the max money that we can wrap with this example. Now step 0. Is our problem a DP problem? Let's see if it is by running some thought experiment. The first scenario is, I can choose not to wrap any houses. Then, the max money that I have is 0. The second scenario is, I can choose wrapping the first house, skipping the second one, and wrapping the third house. That's gonna give me $5. That is the second scenario. By the two thought experiments, we can see that running different scenarios gonna give us certain amount of money that we can wrap with that scenario. And if we can have all scenarios, we can choose the best one, which is going to give us the max amount of money that we can wrap. And running all scenarios, then choosing the best one is a DP problem. So yes, our problem here is a dynamic programming problem. And then we can use SESV to easily solve our problem. Next, we already know our problem is a DP problem. Now we're going to use SESV to solve this DP problem by hand drawing all scenarios, or in other words, running all its courses. So if we start here at the first house, we have two choices. The first one is we can choose to wrap this first house. The second choice is we're not going to wrap this house, we're going to skip this house and run to the next house. So that's a no. If we choose to wrap this house, we're going to have the money of $1, and then we move to the next house. What is our next house? Well, the rule is we cannot wrap two adjacent houses. So if we choose to wrap this one, the first house, then the second house is not a choice anymore. That means the next house we're going to decide is house 3, which is this house here. Now when we at house 3, we still have the same choices. That we can wrap this house, or we choose not to wrap this house. If we choose to wrap house 3, we're gonna get $4. Combining that with $1 we already have, gonna give us $5. And after wrapping house 3, we run out of houses to wrap. If we run out of houses to wrap, that means our wrapping is done. And what we're gonna do is we're gonna count the money and celebrate. And this is one of our final state. So we're gonna stop here. Now we're gonna continue with our choice here. If we are here and we choose not to wrap, we also run out of houses to wrap. And the money that we collected is $1, which we have from wrapping the last house. And as we had no houses to wrap, this is one of our final state. Now we're going to finish this branch 2. That is where we are at house 1, and we choose not to wrap. That's going to lead us to no money here, and we're going to be at house 2. When we at house 2, we have two choices. We either can wrap this house or not wrapping this house. If we wrap this house, it's going to give us $3. And after wrapping house 2, we cannot wrap house 3 because we cannot wrap two adjacent houses. So we're going to move past house 3. That is where we have no houses to wrap left. And that is one of our base cases. Now if we use house 2, and we decide not to wrap house 2, we can move on to house 3. Now we at house 3, which is right here. We have no money here because we decided not to wrap and not to wrap 2 times. And when we are at house 3, we also have 2 choices. That if we want to wrap this house to get $4, or we don't want $4 and skip this house. If we choose to wrap this house, we're gonna have $4 plus 0 so far. That's gonna give us $4. And we also run out of house to wrap. So this is actually one of the base cases. The last scenario is we're at house 3 and we decide not to wrap. That means we have no money from house 3 and we also run out of houses to wrap. That is a sad day for the wrapper, but it's also a scenario that can happen, and that is also one of our final states. Now we have all possible scenarios listed in front of us. We're gonna choose the best scenario asked by the problem statement, and the problem statement wants to find out what is the possible max money that we can have. So that's easy. We have $5 here, $1 here, $3 here, $4 here, and $0 here. So this is what we want. And it's the correct answer. By wrapping house 1 and house 4, we have $5. And $5 is the most money that we can have from here. What we just have done is solving a DP problem with SESV by hand by drawing all scenarios. Next, we're gonna turn this hand-solved solution into code. Turning this solution tree into code is gonna be an easy routine for you. So I'm gonna do this a little bit faster this time. First, we're gonna have a wrapper function called wrap. Second, always name your recursive function depth of search to emphasize the importance of depth of search in DP. Third, state parameters, which is the number that we're gonna put in our recursive function. And we can see here, to decide the state of our system, we need to know which house that we are at, which is the pointer of this array. I'm gonna call it I, and I always start from 0. Next, number of recursive calls. We have 2 choices, yes and no. So they're gonna be 2 recursive function calls. Next, changing state. If I wrap the first house, then the next state is gonna be at the third house. That means here, we're gonna have I plus 2, because we're skipping the house in the middle. And this is the house after the adjacent house. Second choice, if we choose no, our state is the next house, which is I plus 1. If we're not wrapping the first house, which is at 1 here, our next state is gonna be at the second house, which has $3 here. And this is the state for adjacent house. Next, base cases. We're gonna stop the branching when we run out of houses. And that is when I is greater than or equal to the number of houses. We're gonna stop all the branching then. With this code, we are now able to recreate our tree, which is our solution here. And to test if this code is correct, we're gonna print out the nodes, which is the value of the house and the index of the house. Now if we run our code, we're gonna check the output of the nodes here with the node discovery deficit pattern on the tree. On the tree, we're gonna have 1, 4, and this is our bound, so we're gonna have nothing here. So the first step is gonna be 1, 4, and that's what we have here, 1 and 4. The second step, the index go out about 2, so we're not gonna see anything. The next step is gonna be 3, and then nothing, so that's what we have here. The next depth is going to be 4 and then nothing, and that's what we have here. And the last depth, we don't have a node, so we have nothing on the console. So the output of the nodes from our code has correctly recreated this tree, and by comparing our code output with the depth of search node collection of the tree, we know that our code is correct. Next, SESV step 2. We're going to calculate the information asked by the problem statement. Bottom up. We always do bottom up, so we can cache later in step 3. And you can see if we keep following the deficit node collection, we finish a depth, and we can collect the money along that depth. but we're gonna do bottom up. So at each depth, we're gonna return 0 because we out of houses to rob. And at each branching node, we're gonna return the money of that node with the bigger money returned by the two choices. That means we're gonna return 0 here. And then we're gonna return the bigger sum here. And we're gonna return everything here. So if we run our code, we're gonna have 5, which is the max money that we can rob with our particular input here. Now we have a working solution, but remember, without a cache, the time complexity is really high. We have two choices and it's go n level deep, so it's gonna be 2 to the power of n time complexity. We're gonna reduce this time complexity in step 3. Next, SAMDB step 3, we're gonna cache distinct deficit calls to reduce the time complexity of our algorithm. Now if we look at our tree, we're gonna see repeated subtree, like the subtree in the green circles here. And that is where we're calling the same deficits with the same input parameter, which is deficit 2 and deficit 2 here. And whenever we see repeated calls, we can catch it when we see it the first time. For example, here we cache deficit 2 equal to 4. And when we see it again here, we can look at the cache and just return 4. Our cache key is all the parameters describe the system state, in this case at only n, and our value to cache is the return value of this function. So first, we're going to introduce the cache. Second, if we see something already cached, we return it. Otherwise, we're going to calculate as normal. Then we're going to put the return result into the cache, and then we're going to return the result. So if we run our function, we're going to have 5. It's the same result that we have in step 2, but the time complexity of our algorithm has greatly improved. From O2 to the power of n, with the cache, it's got reduced to O of n, where n is the number of the houses. We can test that by running our solution without the cache and with the cache. So if we run it, of course we have the same result of 2 solutions. The no cache solution takes 1.2 seconds. The cached solution takes 0.1 millisecond. We can also test our solution with Leetcode test cases, and as you can see, our solution passes all test cases and got accepted. Our quick summary. The characteristic of problem that can be solved by SAMSDP. It is obviously dynamic programming problems, which is the multi-stage decision-making processes. The input characteristics, it can be any, it can be array, string, or graph. And our go-to solution to solve these kind of problem is SAMSDP. And the time complexity of the solution will always be the number of states created. If you find this tutorial useful, profoundly useful, then make sure to follow SESV tutorial, like, share, and subscribe to our channel, because dynamic programming is a mysterious subject with a lot of software engineers and algorithm learners. Until now, we have a solid way to solve DP problems. So if this is useful to you, let's help the world to demystify DP with SAMSDP by like, shares, and subscribe to our channel. It's gonna make YouTube algorithm to spread the video much faster. I also love to hear your story and how this course can help you to learn dynamic programming in particular or become a software engineer. So come say hi on LinkedIn. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.